Hey everyone, in my absence today I'm just going to run through a quick video to get through the basics of what we would have learned today. Watch this video on your own time and then spend the rest of the time working on the worksheet or the UT as you'd like. We'll start today by asking this question: of the four wires shown below, long, short, fat, skinny, which one would allow the most charge to flow through given the same voltage conditions? Go ahead and think it through here. Pause the video if you'd like. The answer, of course, well, maybe not of course, is going to be C. And if we think about it, it's two reasons. One is that it's the shortest. The less material that you have to go through, the easier it is for the charge to pass. And the other one is the surface area. If a charge moves along the outside, if we have more surface area, that means more charge can move. So more charge can move, and it's easier for it to do. So that would make for the easiest passage. That has to do with something that we're going to call resistivity, which is how you determine the resistance of things that are not known as being resistors, like your toaster wires or your motors or anything else that you're using with electricity. Wires themselves have resistance, and we're going to use this equation to calculate the resistance of the thing. We have L over A, which you see right here. L over A is just the length of the wire, so the longer it is, the more resistance it has, divided by the area, which means the bigger it is around, the greater the cross-sectional area of the wire is, the less resistance it has. And then this Greek letter rho, that's R-H-O, rho, is it just has to. It's called the resistivity. It's the material that the thing is made of. If it's made out of a certain material, it will be more or less resistive. The combination of these three things gives us the resistance of the wire. So here is a list of things that have resistivity that are known. This is experimentally determined. It's like mu, or it's like kappa for capacitors. It's just a thing that we know and that you'll get. The one that we'll be using today the most is this one right here, the copper. We use copper wires all the time, 1.68 times 10 to the negative 8 ohm meters, and that's just how resistive it is per unit length there. All right, so let's start thinking about this. If we have some wire that has a resistance of R, if you stretch it out so that it's twice its original length, then how would its resistance change? Would it be the same? Would it be bigger or smaller? Take a second and think about that. Pause the video, and when you come back, we'll talk about the answer. Okay, we're back. You should have some answer in mind. The answer has to do with how the length changes versus the area. If the volume of the wire is calculated by the cross-sectional area times the length, then if we double the length, we must cut the area in half, because we have the same volume of wire that we had before. So we have twice the length, half the area for the same amount of volume, as you can see on the right there. If we apply that to our resistivity equation, we turn L to 2L and A to half A. Since we're dividing by half A, that's kind of like multiplying by 2. So we end up with 4 times the resistance. And if we make it longer, that's more resistance, and if we make it a smaller area, that's also more resistance. So doubling the length will actually quadruple the total amount of resistance that we get, just because of how it changes the length and the area. Let's talk about a copper wire. If we have a copper wire that's typically about 1.5 millimeters in diameter, it's a circular wire, so think about how to find the area of a circular wire. Then I want to know how long it would be to have an ohm of resistance. Again, pause the video right now. I'll wait for a few seconds, give you a chance to pause it. Try it yourself, and then come back and we'll take a look at the answer. All right, so you should have an answer in mind right now. I'm going to start with this, rho L over A, to find the resistance of this wire. Now, I know the resistance is going to be 1. The area of this thing is 1.5 millimeters. Divide by 1,000 to get it into meters, divide by 2 to get it to a radius. Pi r squared is the cross-sectional area, which you can see there as some millionth or so of a square meter. And then we'll just do rho L over A, where I know R is 1, rho is given because it's copper and the area we just calculated, and we'll calculate L, and we get about 105 meters. So a pretty long wire, 100 meters of wire for every ohm of resistance. That's a pretty low rate, but there is a little bit of resistance in every wire. In this case, an ohm per 100 meters. Okay, so that's the first thing that we needed to talk about. Of course, there would have been lots of cool stories and fun things to say, but here we are. The second thing we have to cover in the next 45-minute period is this idea of power and energy. Of course, we talk about those two words like they are the same thing. We talk about power plants that deliver energy to houses, but power and energy are very different things, and we need to understand the difference. The thing to remember is that power is an amount of energy per time. How much energy do we use in an amount of time is the amount of power. So something like a 60-watt light bulb uses 60 joules of electric energy per second. 60 joules per second is 60 watts. Power is the rate at which we use energy, and those units are in watts or joules per second. That means that energy is what I like to call power time, right? Energy is power for an amount of time. So if I operate at 1,000 watts for an hour, that means that during that hour I was operating at 1,000 watts all the time. That would use an amount of energy, and that energy we can calculate in a couple of ways. One, we're going to use this equation: power equals volt amps. Let's take a look at why. We know a volt is a joule per coulomb. It's an amount of energy per charge, and we know that current is a coulomb per second. Well, if we take a look at both of those together, we see that the coulombs cancel out, and I'm left with a joule per second, which is a watt. So if we talk about how much energy each charge has and how many charges are passing by a certain place, we can talk about how much energy is being delivered in a certain amount of time. So that is going to be the way we define this. Power equals V times I. Now, we can use Ohm's law. We can substitute that in. And we can remember that voltage equals I times R. So if I plug that in, I'm going to take voltage here, and I'm going to substitute it in for I times R, and then multiply it by I to get power, and I get I squared R. And I can do the same thing with I, which is V over R, and I get V squared over R. And we can say that these three equations are like the three power equations, when really they're just power equals V times I with Ohm's law substituted in for either V or I. But those three, we can use all three of these to get power. It depends on what you have. If you have current, resistance, and voltage, any two of those will get you power if you use the right equation. Of course, on your equations sheet, I will only give you power equals V times I, and you have to use Ohm's law to solve for the other two, but just be aware that you can. So, for example, if I'm looking at this and I have a battery that's powering some light, and I know it's a 40-watt light and it's rated for a 12-volt battery, I say, well, here I have power and voltage, and I'm looking for resistance. So I'm gonna choose the power equation that gives me those three together. I'm going to say power equals V squared over R, and if I'm calculating the resistance, I can say V squared over P is resistance. 12 squared over 40 is 3.6 ohms. That is one way of thinking about electric power that we'll be talking about a lot. Another one is our electric bill. This is my actual electric bill from last year. You can see the dates right there. Right there, it's actually talking to me. This is my actual house. You can see that I used 280 of something that's really kind of strange. This little thing here, a kilowatt hour. If you remember that energy is power time, power for an amount of time, a kilowatt hour makes a lot of sense. A kilowatt hour means I'm running at a kilowatt, 1,000 watts, for an hour. If you turn on a 1,000-watt blow dryer and leave it on for an hour, it uses an amount of energy, and that amount of energy we're just going to call very creatively a kilowatt hour. And if you look here, I paid $38 for the 280 kilowatt hours that I used that month last year. I'm going to add this $606.09 because they did something there for me. But if we add that back into the cost, I paid some $42, $43, $44 for this. That gives me 16 cents per kilowatt hour. So 16 cents per kilowatt hour is what I pay today, right now. Like every time I operate something at 1,000 watts for an hour, it costs me 16 cents at home. And we're going to talk now about maybe the costs of what it takes to run the electric appliances in your house per kilowatt hour, and we're going to talk about how to calculate that. So I don't know if your mom has ever told you to turn off the lights. I do the same. It's just what happens when you become a parent. You yell at your kids to turn off the lights. But it's dumb because we're about to find out how much that's actually going to cost you. So let's say it's a 60-watt bulb and you turn it on and you leave it on in your room for like an hour, and your mom comes and says, "How many times have I told you to turn off the light?" Let's do the calculation of exactly how much that actually costs. To calculate kilowatt hours, we have to do energy is power time. So we're going to say energy equals power time, and we have 60 watts for 1 hour. That's the power and the time. Now, I want to convert that into kilowatts, so that's 0.06 kilowatts in an hour is 0.06 kilowatt hours of energy. You with me here? Power times time, and we're just going to keep them in kilowatts and hours instead of converting them to regular old joules, because we pay for kilowatt hours, not joules. So we're just going to say, instead of watt seconds, we're going to say kilowatt hours. It's sort of the same idea. But that 0.06 kilowatt hours at 16 cents per kilowatt hour costs me 1 cent. So running a 60-watt bulb for an hour costs you a penny. So if you left it on all day, it would cost you a quarter. Now, the real rule, and let's be absolutely clear here, the actual rule is do what your mom says, but in actuality, it does not cost all that much to leave the lights on. It's almost negligible, but do what your mom says. And if you tell your mom, like, I don't have to turn off the lights because Mr. Gibson said so, I will completely disavow all knowledge of this recording, just so we're clear. So why don't you try one? Let's say I've got an electric heater that draws 15 amps on a 120 volt line, and that's a standard electric space heater. Tell me, how much does it cost to run it for 30 days at 3 hours a day? All right, I turn it on every day for 3 hours, and I do that for a 30-day month. How much is my electric company going to charge me for that? Give it a shot. Try and find out the power and find out the kilowatt hours that you would spend in 30 days, and then figure out how much that would cost you. I'm going to pause here for a second. You pause the video, give it a shot, and see what happens. Okay, we're back. You should have a number in mind. Let me show you how I'm going to do it. I'm going to say power equals V times I, right there. And that's the 120 volts plus, times the 15 amps gives me 1,800 watts. That's 1.8 kilowatts. So it costs me 1.8 kilowatts, and on any given day, I run it for 3 hours. But I do that for 30 days. So I'm going to say number of kilowatt hours is 1.8 times 3, and that's the number of kilowatt hours in a single day, and then I'm going to multiply that by 30 days, and I get 162 kilowatt hours, which costs me 25 bucks at 16 cents a kilowatt hour. So that would be, again, how you calculate it. Again, I'm going to run this through for you one more time. You find the power, you convert it to kilowatts, you multiply by the amount of time. So this is power time right here, right? That's power, and that's time. And that power time gives you kilowatt hours. Don't convert to SI units. Stay in kilowatts and hours, and then you can convert to cost. Another thing is fuses, right? Our fuses protect us by shutting off the power when we ask for too much current, which might melt the wires in our house and start a fire. So let's take a look at this. I want you to use the power equals V times I equation to figure out if all of these things on the same circuit would blow a 20 amp fuse. Just figure out how much current you're asking for here. Go ahead and give it a shot, and we'll be back in a few seconds. Okay, you should have an answer. Let's go through this item by item. If I is P over V, that's just the power equation rearranged, I can figure out how much current each thing, the 100-watt light bulb on 120 volts from our house gives me, less than an amp. Our 1800-watt heater draws 15 amps, 3 amps from the stereo, 10 amps from the hairdryer, and all I have to do is add all these up, which when I do gives me 28.75 amps, since my fuse is designed to run on 20 amps, and I'm taking 28 amps, that means in this case the fuse will blow. So there's a couple of ways that we can talk about power. Go ahead and try these out. You'll also have plenty of problems to try in your homework, so you can try these out, and we'll talk more. I'll do a quick review, and we'll talk more about this when we get back from the weekend. Have a lovely day.